Okay, hello cloud gurus. How y'all doing? Welcome to Architecting to Scale. Now, if we consult the blueprint, architecting to scale or scalability fits in two general areas, the new solutions as well as the existing solutions. But there are some things about scalability that you need to pay attention to with regard to cost effectiveness as well. So we're going to spend some time exploring what AWS has as far as scalability, and let's get started. One of the things you'll hear about if you've been around architectural circles for a while is this concept of patterns. And we're not talking about patterns like how you would make clothing, but really patterns are just suggested ways to help design architectures. One such pattern is something called a loosely coupled architecture, and that just means that the components can stand independently without requiring very much knowledge about the inner workings of the other components in a chain. Now, loosely coupled architectures have some very good benefits when it comes to scalability. First, it introduces layers of abstraction, and this permits more flexibility and interchangeable components because the parts and pieces don't have to know about the other parts of the chain. Now, one of the important aspects of a loosely coupled architecture is that the work units are more atomic. They're more isolated, and that lends themselves better to scaling independently. Let's take a look at a process as an example. Okay, right here we have a tightly coupled process. We have step one, step two, and step three, and we've timed them, and step one and step three take 5 seconds, but step two takes 20 seconds to happen. And unfortunately, our goal is something less than 15 seconds. So right now, we can't achieve our goal. One of the ways that we could achieve our goal is provide step two with more computing power. So thereby turning those 20 seconds into 5 seconds by allocating more resources. So then we're within our 15-second goal. The problem is with a tightly coupled architecture, you have all this excess because you can't just scale one step. You have to scale the whole system. And it's going to be general waste. Now, in a loosely coupled process where we separate out step one from step two to step three, we can still have the same resource allocation, but it's right sized to each individual step. So in this case, maybe step two, we would scale vertically, meaning we'd give it more computing power and RAM to take that 20-second time down to 5 seconds. Now, if the application supported it, we could also use parallel processing, and we could have 4 different instances working on step two at the same time. And this is called scaling horizontally. I'll explain this more in a second. So here are the differences between scaling horizontally and scaling vertically. Horizontal scaling is really just adding more instances as the demand increases. Vertical scaling is just adding more CPU and RAM to an existing monolithic instance as that demand increases. Now for horizontal scaling, you shouldn't require any downtime because you're just adding and removing additional instances. Vertical scaling, on the other hand, at least on AWS, does require downtime because you're going to have to reprovision the instance type to something larger or smaller, and that requires a restart. Now, horizontal scaling is automatically supported using auto-scaling groups, but vertical scaling, there's really no good way to automate that aside from maybe a custom script. And horizontal scaling on AWS is theoretically unlimited. You could just keep adding instances to make your process faster and faster until you've used up all the instances that AWS has. Now, vertical scaling, on the other hand, is limited because AWS only has instances that are so big with so much RAM and so much CPU. So to scale out, we would add an instance. To scale up, we'd add resources to an existing instance. To scale in, we'd remove that instance that we scaled out. And to scale down, we'd remove CPU and RAM. Here's an architecture where we can see the difference. In this particular case, we just have a very simple messaging process architecture, and we have an M5 2x large instance that processes those messages and saves them to S3. We could alternatively architect it like this, where we have 4 M5 large instances. Now in this case, it's roughly the same cost, whether we go with a M5 2x large or 4 M5 larges. So why would you want this scale out architecture in preference to one large instance? Well, let's look at the economics. A lot of times our demand isn't consistent. So in this particular chart, the blue line is our demand. The green bars is the large instance, and the yellow bars are our auto scaling group. So as demand changes day by day, we can scale in and scale out to meet that demand. Whereas if we have just one large instance, it's going to be the same price regardless of what our demand is. So then looking at the dollars, if we don't have any scaling, it's going to cost us $46.08 for those 5 days. If we do implement auto scaling, we're down to $32.26, and that's a savings of $13.82. Now I know these might not seem like big numbers, but if you multiply these by very large enterprise systems over the course of time, then we're talking big money. But even still, if somebody's willing to give me $13.82, I'm not going to give it right back to AWS. I have plenty of other things that I want to spend it on.
Let's talk about auto scaling. Now, there are several services on AWS that use the term auto scaling, and some have been released recently and some have been around a while. And it was pretty confusing to me, and I wanted to spend some time breaking these things down so that hopefully it won't be so confusing to you. And I'll be using this diagram a few times in this lecture to help illustrate how different services work together. So first and foremost, Amazon EC2 autoscaling has been around forever, and it does what the name says. It's mainly focused on EC2 and really nothing else. And we can set up scaling groups for EC2 that, based on health checks or metrics, spin up more instances as we need them. Now, another space where AWS uses the autoscaling terminology is in something called application autoscaling. And the idea here is that it's an API that's used to control scaling for other resources than just EC2. Like, for instance, Dynamo, ECS, EMR, all those services have their own specific auto-scaling capabilities, and application auto-scaling just kind of rolls those up into one API such that you can control them through one API call, for example. Now, there's another service called AWS auto-scaling, and the idea here is it kind of presents a bird's eye view of all your auto-scaling. It's really focused on more holistically representing the auto-scaling across the different layers of an application, for example. And we'll take a look at this later, but there's a specific console where you can access AWS auto-scaling. Now, first, I'm going to talk about EC2 auto-scaling groups. And the idea here is they're just there to provide horizontal scaling. In other words, scale out. And remember, when we're talking about scale out, we're talking about adding more instances. Generally, it's the same type of instance. If we're talking about scale up, that means we're replacing that smaller instance with a bigger instance. But auto-scaling groups scale out for us. And they're triggered by some event or some threshold that we would set in a auto-scaling policy. And we have 4 scaling options. The first is just maintain. That just keeps the same number of instances, the same minimum number of instances running. Then we have manual, which is what you might expect. We can go out there and specify we want a maximum of these instances running, a minimum, or a specific number. We can also scale based on schedule. So if I know a certain time of the week is very busy, then I can scale during that time of week and then scale back down after that. Then we have dynamic, which is based on some sort of metric that we collect off the instance or the instances that helps us decide, do we need more instances? And to use EC2 auto-scaling, you need to set up an auto-scaling group with something called a launch configuration. And this contains all the details that the auto-scaling process is going to need when it tries to launch a new instance, including the AMI and which VPC you want it launched in, if you want it attached to an Elastic Load Balancer, and that sort of thing. Something else I'll call out here is something called a health check grace period. And that is just a time period that the scaling policy will allow that system to spin up and become healthy before it starts alerting on potential health problems of that instance because maybe it's not responding. So for example, if you're spinning up a new instance, sometimes it takes time for that instance to boot up and maybe load up a web server, for example. And so if you're pinging on that port 80 web server and it doesn't respond, that could be a problem, but you want to allow enough time for that process to come up and start responding to those pings. Now, inside the launch configuration, we can define how we want to scale. Do we want to maintain a certain number, or do we want to scale based on a metric? And the scaling types we have available, I'm going to just go through them quickly right here because I have some examples. So if we want to maintain, we just need to maybe keep 3 instances running. If we're doing it manually, we can use the console or the CLI to specify a specific number of instances that we want running. We can schedule it based around a certain time, or we can use a dynamic scaling type that's based on maybe CPU utilization over a 5-minute or 10-minute period of time. Now, within the dynamic space, we also have something called EC2 auto-scaling policies. And this is just kind of a strategy that we can decide how that dynamic scaling is going to work. So we can have a strategy of trying to track to a certain target. So in other words, if the CPU gets above 70%, for example, maybe we add instances so that we can disperse the load across more instances. We also have a simple scaling policy, which is a pretty simplistic way of scaling. It just adds more instances and it waits the health check period or the cooldown period. And we'll talk about the cooldown period here in a second. Then we have the step scaling policy. Step scaling can be used to implement some more sophisticated logic. Now, there is this concept of cooldown for scaling in EC2. The idea behind the cooldown period is it gives your resources time to stabilize before automatically triggering another scaling event. And there is a difference between health check grace period and cooldown period. The idea behind health check is that it gives the resources an amount of time to come up before we start checking their health status. Cooldown, on the other hand, is designed to allow the resources to come up to speed and start absorbing the load. And that may be a different amount of time than the amount of time we're willing to wait before we start checking for health. Now, the default cooldown period is 300 seconds, and it automatically applies to dynamic scaling and is optional with manual scaling, but it's not supported right now for scheduled scaling. And the reason for that is because if you're using scheduled scaling, then generally you have a time-based schedule that you're using versus any sort of metrics or events that you're going to need to let settle before the cooldown period comes into play. Now, you can also override the default cooldown period. An example of when you might want to override the default cooldown for your auto-scaling group is maybe in a scale down policy. So maybe your scale down policy just terminates instances so you wouldn't need to wait as long to evaluate whether you could terminate more instances, as you'd have to wait until new instances were fully spun up. So here's an illustration of why cooldown period is useful. If we didn't have any cooldown period, we could trigger a bunch of scale events and suddenly have a whole lot of instances that we didn't really need. With a cooldown period, it's kind of like a sanity check. It waits a little bit, tries to figure out, okay, is the one instance that I just added, is that enough? Or do I need to add another instance? We can also trigger scaling events based on external conditions like queue size in an SQS queue, for example. And this diagram shows a common architecture one might use to process through things in a scalable asynchronous manner. Now, back to our diagram of auto-scaling confusion. We've just talked about EC2 auto-scaling. Let's move on to application auto-scaling. Now, if you remember, AWS application scaling is really just an API that can be used for some of the other services in AWS. And it has similar scaling policies as well. We have the target tracking scaling policy, which tries to maintain a certain metric. We have a step scaling policy, which can scale up at a fixed level or fixed duration. And then we have a scheduled scaling policy, which is time-based. And we can manage some of the application auto-scaling as well as the EC2 auto-scaling through one common console, and that console is called the AWS Auto-Scaling Console. It provides a pretty nice way for us to gather all the resources and manage scaling in a more holistic way versus doing it at each and every stack layer in each and every subservice that we're using. And it provides some high-level scaling strategies that are phrased more in business terms than technical terms, but you can always dive into the custom option and get down into the real nitty-gritty of defining your scaling. A really neat feature that I like is something called AWS Predictive Scaling, and it uses some machine learning algorithms and some data analysis to try to predict when you might need to scale up or scale down. Now, you can either use this information to have AWS automatically scale for you, or you can just use it as a data point and control the scaling yourself. Also, if you're worried about privacy or AWS tracking your information, you can opt out of this data collection and you won't be provided with this option. So in the context of the exam, just know the concepts of autoscaling and know the difference between autoscaling, EC2 autoscaling, and application autoscaling.
Let's talk about AWS Kinesis. Now, really, Kinesis is a collection of services. It's designed around processing streaming data of various types. And the data is processed in shards. Each shard is able to ingest 1,000 records per second. And the default limit to the number of shards you can have is 500, but you can request that limit be raised to whatever you think you might need. When a piece of data comes into Kinesis, it's called a record, and that record is going to consist of a partition key, a sequence number, and whatever the data is that you're sending in. And the data can be up to 1 megabyte in size. Kinesis should be thought of as a transient data store. Its default retention period is 24 hours, but it can be configured up to 7 days. But really don't treat it like a persistent data store. It's just a way to gather in data at a very high rate of speed, and then you have to do something with that data, be it write it out to a database or S3 or process it through Lambda. So you should keep that in mind. Now, as I said, there's various flavors of Kinesis. One of the newer flavors is the ability to process video streams. And this is probably not going to show up on the exam, so we're not going to spend too much time talking about this particular option. We're going to focus more on the data stream, which allows us to ingest a high volume of data and then process it through a variety of ways. We also have Firehose that allows us to automatically send that data to a variety of landing spaces. So if we don't have to process it right then and there, we can land that data in some other system or service. A very interesting feature of Kinesis is we can actually do analytics on the data as it's coming in. So we don't necessarily have to wait until it gets landed in a data warehouse before we start looking at analytics on the data. As I said before, Kinesis processes things in shards, and you can think of shards as lanes in a highway. The more lanes in a highway, the more traffic can go through at one time. So the more shards you have, the more traffic can go through. So in this case, we have a certain number of shards. We have our data coming in. That data gets divided up into those shards. And then ultimately it gets passed on to either Firehose, where it gets landed maybe in S3 or Redshift, or we can have applications called consumer applications that read these shards and pick up the data, and then they can process it. Something important to know about how Kinesis processes data is that each shard is given a partition key. Now, I've truncated the partition keys here, but really it's a 128-bit MD5 hash, and it's unique to each shard. Additionally, each piece of data as it comes into the shard gets assigned a sequence number, and these numbers are always increasing. So you can use the sequence number inside a given partition key to decide the newness relative to some other piece of data in that same shard. But notice sequence numbers can be duplicated across shards. So to uniquely identify your data, you really have to use that partition key and that sequence number. Here's an architecture for a Maker Lab I did for A Cloud Guru not too long ago. It involves using the Twitter API to bring in tweets via Kinesis, and then using Firehose, we landed them on an S3 bucket. Once they hit the S3 bucket, we then triggered a Lambda routine which unpacked that tweet. We stored it in a DynamoDB database. We also did some text analysis to try to figure out whether that tweet was friendly or not so friendly. If you want a hands-on exercise for using Kinesis, I recommend going and checking out that Maker Lab. DynamoDB scaling is really divided into two dimensions here. One is throughput. That's our read and write capacity. And then we also have size. Now, any single item can only be 400K, but we can store as many of those 400K items as we want to. There's basically a limitless amount of space that AWS gives us. So if we recall back to our lesson on DynamoDB, we have this concept of a partition. That's a physical space where DynamoDB stores the data, and these are divided up into 10 gigabyte chunks. We also have the partition key, and that's that unique identifier. It's also sometimes called a hash key, and you'll see why later. Then we have the sort key, and in combination with the partition key, you can create a composite key that defines how that record gets stored and how it can be retrieved. And sometimes this is called a range key. Now under the covers, Dynamo scales out by adding partitions. And here's the formula for how we decide how many partitions we get. So there's two dimensions. One's by capacity, and the other is by size. So by capacity is how many read units and write units we've provisioned. And then for size, it's how many 10 gigabyte chunks we take up. And so our total partitions are going to be decided by the maximum of either the capacity calculation or the size calculation. Let's look at an example. So in this case, I have a 10 gigabyte table. I have 2,000 read capacity units and 2,000 write capacity units. So my partition calculation by capacity would be 2.66. By size, it's 1. And so my total partitions are going to be the max of either of those, which is 2.66. But because I can't have a fractional partition, I get rounded up. So I'm going to have 3 partitions. So in this case, note that the read and write capacity has been equally allocated across our partitions. Now, AWS does allow some burst capacity. It allows me to exceed some of that read and write capacity against a single partition if I'm not using that in those other partitions. But really, we should design our partition keys around trying to avoid this whenever possible. And I'll show you the problem that we'll run into. So let's look at how DynamoDB actually decides how to land hashes on the different partitions. Now, as you remember, when we talk about the partition key, it doesn't get stored as the text value that you pass in. It gets translated into a hash value. So if we have one partition, all the data is going to land on that same partition. So there's really not much we can do from a spreading the load around standpoint. Now, if we increase our read capacity or write capacity, or we reach that 10 gigabyte cutover, now we have maybe 2 partitions. And in essence, DynamoDB just divides the data down the middle and says 50% is going to go to partition 1, 50% is going to go to partition 2. And it's based on the hash value or the partition key hash. And if we go to 3 partitions, it's going to do the same thing. It's going to divide them into 3s. So you can see why it's beneficial to have a partition key that has a degree of variability in it for the data, because that's going to help us equally spread the load across the different partitions. Let's take, for example, a scenario where we've designed a data collection system where we're getting data from sensors, and we've chosen to use a partition key of date. Well, the problem is we get a lot of sensor readings every day. So from a write perspective, we're going to be hitting that same partition because when the date gets hashed out, it's going to be the same. So we're probably going to be consuming all of our write capacity against that one partition pretty quickly, whereas partition 2 and 3 go unused. Similarly, when we go to read it, we're going to be slamming a single partition and not distributing that load across all the partitions. This is known as a hot partition or a hotkey issue. Now, alternatively, what we could do is choose to make sensor ID as the partition key, and then use date as the sort key. Now, when those sensor IDs get hashed out, chances are they're going to be landing on different partitions. And so this makes better use of our write capacity. Additionally, it makes better use of our read capacity because we're going to be able to spread that read load across many partitions. Now, DynamoDB also has the ability for us to specify auto scaling. And when we reach a certain target utilization, we can scale up our provision capacity for read or write units. In essence, it looks like this. We're going to specify a certain provisioned limit. And once we reach that limit, the DynamoDB configuration is going to trigger a CloudWatch notification, which is going to tell our application auto scaling process to go update the provision capacity on that DynamoDB table. And we could also have an SNS notification go to us and let us know that that's happening. Now, there are some things to note about auto scaling for DynamoDB. It uses this target tracking method to try to stay as close to possible as that target utilization. And right now, there's really no good way to scale down if that table's consumption drops to 0. And that's because DynamoDB doesn't know if it's just simply not being used or truly the demand is gone for good. Workaround number one is we can just send requests into the table until it auto scales down. So we could keep requests going at a very minimal level. And then DynamoDB will finally figure out, okay, the average load has dropped, so I'm going to scale down. Workaround number two is that we can manually reduce the max capacity to be the same as the minimum capacity. So in essence, what we're just saying is scale down to some minimum capacity that we had before you decided to scale up. Now, autoscaling also supports global secondary indexes. And this makes sense because you got to kind of think of global secondary indexes as just a copy of the original table, just indexed or keyed differently.
An alternative to this is something called on-demand scaling. And it's really just designed to be an alternative to the auto scaling. And on-demand scaling is just going to give you capacity whenever you need it without having to provision that capacity in advance. The downside is that it costs more than traditional provisioning and auto scaling. There's a bit of a premium you're going to pay for that luxury. And this might be a good thing if you're going to market with a new app and have no idea of the usage pattern, and you don't want to risk that scaling lag. But however, in the long run, you might be able to save some more money by figuring out your regular provisioning needs and use more traditional auto scaling methods. Now, I should mention there's a service-oriented feature called DynamoDB Accelerator, or DAX. And DAX is an in-memory cache that sits in front of your DynamoDB table and just provides caching in a format that's compatible with the DynamoDB API. So in those cases where you just got no time for millisecond response time like you usually get from DynamoDB, you can move on up to microsecond level response time using DAX. Now, some good use cases of DAX might be when you really need just the fastest lookup time or the fastest response time, especially if you have very read-intensive applications. Now, you probably wouldn't use DAX in the case where you have a very write-intensive application, because remember, caches are good at reading, not so great at writing. And also, if your application happens to cache stuff locally, then it's kind of a waste to use DAX in that case.
Let's revisit CloudFront. I call this CloudFront Part 2. So CloudFront, as you know, can deliver content to your users faster by caching content on edge locations. Now, one thing to note is that we can cache dynamic content as well as static content. Dynamic content delivery is achieved by using HTTP cookies forwarded from your origin site. CloudFront supports Adobe Flash Media Server's RTMP protocol, but you have to choose the RTMP delivery method. Now, web distributions, which use the HTTP protocol or HTTPS, also support media streaming and live streaming. And origins can be S3, EC2, ELB, or another web server. And you can configure multiple origins. As a matter of fact, behaviors are allowed to configure different content based on URL path, for example. An example of this might be a WordPress site where we have Route 53 coming into a CloudFront distribution, and we specify the static content is going to be coming from an S3 bucket, whereas our dynamic content can come off a load balancer, which is back-ended with an EC2 fleet. Now there's several ways to invalidate a CloudFront cache. The first method is simply delete the file from the origin and just wait for the time to live to expire. And the TTL is configurable. You can also use the AWS console to request an invalidation of all content, or you can specify just a certain path. You can use the CloudFront API to submit an invalidation request. And there are several third-party tools that allow you to invalidate the cache. CloudFront also supports Zone Apex DNS entries. And what that means is that's just your domain name without any www or any subdomain in front of it. And in this case, scottpletcher.guru is my domain name, and I've pointed it to a CloudFront distribution. And you can see my NSLOOKUP returns the IP addresses of that CloudFront distribution. CloudFront also supports geo restrictions. You might want to do this if you have certain regulatory restrictions or guidelines where you're not allowed to show content or expose content to certain geographies or countries. So I can use this whitelisting and blacklisting capability to restrict or explicitly grant access to my CloudFront distribution. Amazon's simple notification service is so simple, but it's oh so useful. It enables pub sub or publish subscribe design patterns. And it consists of a topic, which is just a channel for publishing notifications. Kind of think about it like an inbox, or more properly an outbox. And subscriptions. Subscriptions are just configuring an endpoint to receive a message that was published on the topic. And the different endpoint options are HTTP or HTTPS, email, SMS, SQS, Amazon Device Messaging, which is Amazon's push notification platform, and Lambda. Here's something you can do with SNS, and it's called a fan-out architecture. That's one of those design patterns that's very useful for doing things in parallel. So we can have some event, maybe a user uploads an item, and it goes into SNS. And then we have this image upload topic. And whenever something gets inserted into that topic, then we have configured 3 different endpoints that get notified of that message coming in. And so we have simple email service, which sends a thank you note back to the user. We have SQS, which takes that image and puts it into a resize queue so it can be worked on by worker EC2 instances. And then also subscribing to this topic is a Lambda function, where maybe we run that through some image analytics. SNS is very useful when you need to do these types of architectures where you have several processes that can run in parallel. And it's a good way to achieve a loosely coupled architecture. Here's a queue. Here is a queue of queues. All right, I know, cut me some slack. This didn't really turn out the way I wanted it to. You see, I'm a child of the 80s, and 2 things that I was really obsessed over when I was growing up was my dirt bike and the arcade. Like many other kids of the 80s, I put every spare quarter I came across into these machines. Dig Dug, Galaga, Dragon's Lair, Russian Attack, they were all great. But there was one that I became particularly obsessed about. It involved this pyramid and this little character, this orange character that had a nose or a snout or a mouth, not really sure. And he would hop along the squares of this pyramid trying to avoid various dangers. And this little guy has even appeared in some recent movies, but unfortunately, he's copyrighted. Now, I thought about maybe using some substitutes, but alas, I just don't think it would be the same. So you got what you got. Okay, enough silliness now. SQS is a highly scalable hosted messaging queue, and it has available integrations with KMS for encrypting messages, which is really useful if you have to maintain end-to-end encryption. Now, SQS should be thought of as transient storage. By default, the message can stay out there for a maximum of 4 days, but you can configure that up to 14 days. But it's not a long-term storage place. And it also optionally supports first in, first out queuing, and we'll talk about this a little bit later. Now the maximum message size is 256K, but you can scale up to 2 gigabytes by using a special Java SDK. And in essence, that stores the message on S3 and then creates the SQS message as a pointer to that S3 message. Now a significant benefit of a queuing pattern is the ability to create more loosely coupled architectures. And this permits portions of the interface chain to tolerate downtime or temporary outages without disrupting the whole chain. It also allows us to govern the data flow better. So let's take a look at an architecture. In this case, we have an ERP system that's generating messages, master data updates. The middleware lands these messages into an SQS queue where they're then picked up by an EC2 worker instance, maybe for some transformation or some augmentation. They're then updated into DynamoDB. Now, suppose the message traffic comes intermittently, maybe 1,000 updates within a few minutes due to a mass change. We could scale horizontally by adding more worker instances and process through that queue faster if we need to. Let's look at a comparison between a standard queue and a first in, first out, or FIFO queue. In a standard queue, we have no assurances that the messages will enter or leave the queue based on when they arrived. And for a ongoing process, this could present some risk. The message stream we're receiving is update 1, update 2, update 3, and so forth. And you can see there's various steps to a process. Update 1 is received, update 2 is sent to warehouse, update 3 is picked, and so forth. Now, if we just have a standard queue, we have no guarantee that we're going to be able to process those messages in order. So if we're continually updating the same record, in this case, the final update would be update 3 picked, which is incorrect because we've already shipped this product. We can switch over to a FIFO queue, first in, first out queue, and that will maintain the order in which the messages were received. Now, the big trade-off in this is that enforcing this order processing means that if a message fails or gets stuck, it's going to hold up all the other messages behind it. And this can introduce some latency or delay in clearing queues. Amazon MQ. I wanted to include that in this lesson because sometimes people get confused around use cases between SQS and Amazon MQ. Now, Amazon MQ is just a implementation of Apache's ActiveMQ. An ActiveMQ is a message broker. It takes care of taking in messages, managing them, and letting other applications via API access them. It functions very similar to SQS, but it's a different implementation of a messaging queue. And in the case of Amazon's MQ, it's fully managed for you, so you don't have to install it on any servers, and it's highly available within a region, so you don't have to worry about that either. Now, it fully supports the ActiveMQ API, and it also supports JMS, NMS, and protocols like WebSockets and MQTT for IoT implementations. And it's really designed to be a drop-in replacement. If you currently use a messaging queue on-premise, maybe IBM MQ or something like that, your application should be able to work with Amazon MQ with very little or no modification. Now, when should you use MQ versus SQS? Well, it's recommended that if you're building a new application from scratch, just go ahead and use SQS because it offers a little bit more feature set and it's more tightly integrated into the other Amazon services. And if you already have an application that uses a messaging broker, maybe in your on-prem data center, you can use MQ to really easily kind of lift and shift that to the cloud.
Now, unless you've been living under a rock for the past 3 years, you've probably no doubt heard about serverless. And if you don't know what serverless is, that's okay because we're going to get into some of those concepts in this lecture. But first, I wanted to introduce AWS Lambda. And AWS Lambda is really kind of a key part of AWS's movement into the serverless landscape and serverless architecture. So it allows you to run code on demand without the need for infrastructure. So you're running functions rather than running whole applications on an EC2 instance or an RDS database, for example. Now it supports all sorts of languages. The most common seem to be Node.js, Python, Java, Go, and C Sharp. There's actually a way that you can create your own language interpreter and use that instead as well. So theoretically, you could run a Lambda function using COBOL or RPG if you wanted to. Now, Lambda is kind of purpose built for creating serverless architectures. And so it's pretty useful at that. And the code is stateless, meaning that once it executes, it goes away. It doesn't really keep up with any sort of data. So you have to keep that in mind when you're designing your applications. Now, there are many other tools that AWS has that can keep up with state, and some of those we've already talked about, some of them we will talk about in the future. But for now, just remember that Lambda really needs to be considered stateless. And if you need to store data, then you're going to need to figure out what your persistence layer needs to be in this serverless architecture. And we can trigger Lambda functions using a variety of different AWS services, including SNS, SQS, S3, Dynamo. Very flexible, very useful in creating event-driven architectures. And theoretically, there's no limits to how many Lambda functions can be executing at one time. So this allows it to scale very, very aggressively and at a very low cost. In fact, the platform that you're watching this video on, A Cloud Guru, is based on this same serverless technology, and it can scale very dramatically. Now, getting into the nuts and bolts and detail of Lambda is a bit beyond this course. On the exam, you're not really going to need to know how to create a Lambda function or do any sort of programming around a Lambda function. We have a ton of other content here on A Cloud Guru that really dives deep into Lambda and serverless, and I would encourage you to check that out if this is something you're interested in. One of the very common architectures that's employed using Lambda at scale is something called a fan-out architecture. And the idea here is that we get a piece of data in or some sort of instruction in, and then we use a Lambda function to then launch maybe 3 other parallel Lambda functions, and those go about their business doing the activity. So the idea here behind this architecture is that you're going to be able to fan out on many different threads to do a worker task. This is a very common and very powerful architecture. Now, I wanted to introduce you to something called the AWS Serverless Application Model. And AWS wanted to make it easy and efficient for people to develop and deploy serverless applications. So they came up with this thing called the Serverless Application Model. And it has this cute little mascot named Sam, the squirrel. Now, they use Sam quite frequently in their marketing campaign around this particular product, and I'm not entirely sure that Sam wants to be involved in this product. They probably took him from the forest and forced him into hard labor writing functions. And they even sent him into space, and I'm not entirely sure that he was on board with that. So hopefully Sam will take the advice of past mascots, which history has not been so kind towards. So some things about the serverless application model that you should know is it's just an open source framework that AWS created, and they published it out there on GitHub, and you can download it and use it. And it uses YAML as the configuration language. Now, if you don't know YAML, that's okay. You're not going to need to write YAML for the exam. Rather, just know that it's a markup language that's pretty commonly used today, and I'll show you an example of what it looks like in the next slide. And AWS SAM includes a CLI that allows you to do certain functions, and we'll talk about that in a second. The cool part about it is that it allows you to test your serverless applications locally before you push them to the cloud, and that's a good thing, especially when you're trying to debug a serverless app. And really just think about it as a sort of front end, a serverless flavored front end for CloudFormation. What it really does is generate CloudFormation templates in the background, and that's what really creates all the resources on AWS. So here's an example of a SAM YAML template for an image processor. You can see that it's pretty simple, defining the runtime, the file to launch. In this case, it's index.js, and some details about the Lambda function. One thing to note about YAML is that it's very picky about spaces. The indentions are part of the format, so do pay attention to those. And using the SAM CLI, we can test and debug our serverless apps locally, which, as I said before, is really handy when you're trying to figure out why your app isn't working just right. And then when we're happy with it, we can deploy it to AWS. And like I said, SAM is sort of like a front end to CloudFormation. So your YAML template gets then translated into a CloudFormation template, which then gets created on the AWS infrastructure. Now, to help you get started on serverless, AWS has prepared a repository of a bunch of pre-made serverless apps that you can just use and model after and learn from. And keep in mind that SAM is different than something else you might have heard of called the serverless framework. Now, they do very similar things. They're all designed to encourage best practices in serverless and make deployment easy. But the serverless framework supports other cloud providers besides just AWS. So if you're just getting started with serverless on AWS, you might want to consider SAM. But if you're considering a multi-cloud strategy, the serverless framework might be a good choice. I wanted to also mention something called Amazon Event Bridge here, as it's along the same lines as serverless architecture design. It's a service designed to hook up various event sources, apply some rules, and then launch other events like a Lambda function or an SNS event. Why use EventBridge given all the other launch event-based services? Well, primarily it was designed to link AWS and third-party applications. So the main value that EventBridge brings is a lot of pre-integrated third-party services that you can very easily hook into the events that some of the serverless services on AWS support. So for example, on Zendesk, if somebody creates a Zendesk ticket, you can then trigger a Lambda function to do something like reset a password or something like that.
So let's talk about Simple Workflow Service. Think of Simple Workflow Service as more of a managed status tracker than a true workflow system. It's not like an ETL tool or a workflow system where you might drag and drop and design flows. It's really just a status tracking system. And with it, you can create some distributed asynchronous systems to help facilitate workflow. It supports both sequential and parallel processing, and it tracks the state of your workflow when you interact with it via an API. And it's generally best suited for human-enabled workflows like order fulfillment or procedural requests. And AWS recommends that for new applications, you might want to look at step functions over simple workflow. There are two main components to Simple Workflow Service. One is an activity worker, and the other is a decider. The activity worker is a program that you write to do some task or job. And using the AWS Simple Workflow Service API, it interacts with the Simple Workflow Service, updating the status of its tasks. Now, the decider is kind of what you would think. It coordinates the tasks and it decides whether to go down one path or another path. So here's an architecture where we're using Simple Workflow Service. So to start out, we take an order that's a worker process. And then maybe we have an on-prem payment processing gateway that we need to send that order to. Then after the payment step has been successfully completed, it updates SWF, and then that triggers a decider task. In this case, we're trying to decide which warehouse we want to ship the order from, maybe based on proximity to the customer or whether we have it in stock in a warehouse or not. Then finally, once that's decided, we can then trigger the ship order worker. Now I say trigger, it's not really the case. These workers have to poll the simple workflow service. They use a process called long polling. And so these programs that you write using the API will continually check to see if there's any activity that they need to do. AWS step functions. Now they're going to appear on the exam probably in the context of Lambda, but it's important for you to know what they are and a little bit about their use cases in compared to some of the other AWS services. So that's what we're going to cover here. AWS Step Functions is really just a managed workflow and orchestration platform. And as you might expect, it's scalable and highly available. And you can define something called a state machine. And we'll talk about this in the next slide. But for now, just know that there's different things that you can do inside that state machine. You can create tasks, steps, parallel steps or sequential steps, decision points like a branching path, or maybe even a timer. And how you do this is using the Amazon state language, which is a declarative JSON language that allows you to configure and document the steps of your step functions. Now, applications can interact and update via the step function API, or there is some direct integration with Lambda and some of the other AWS services. But what's really neat is there's a visual interface that helps describe the flow, and you can also drill into that and find out the real-time status of certain activities. And as you might guess, there's detailed logs captured for all the steps. Now, here's an example of something called a finite state machine. Now, it's more of a computer science concept, but Amazon has used the state machine concept in trying to describe what step functions do. And really, it's just a fancy name for a relatively simple system design. It just means that an object can assume different states or statuses through a process. And in this example, we use an order and what an order processing flow might look like. And the order can take different states as it travels through its life cycle. So it comes in as a new order, then we do a credit check, and that order can assume a canceled state or a verified state. And then once it gets shipped to the warehouse, it has a different state. And then ultimately it gets delivered. Then maybe after a period of time, maybe after our return period elapses, we move it into an archived state, or it could potentially be returned, and then we would do some other stuff to that order. So it's still the same object at the same order, but it's just assumed different states throughout its life cycle. Now, this is an exceedingly simple example of a step function. And this is one of the examples that Amazon provides. And it's simply waiting for a certain timestamp or waiting for a time, and then it's going to send an SNS message. So on the left here, you can see the Amazon state language rendition of this. And then on the right, this is the graphical visual representation that shows up in the console. So we would write the JSON on the left, and the console would interpret that and then render a picture for us. As much as we like to say that event-driven real-time applications are always preferred, there's still the need for good old batch processing. And so Amazon has created AWS Batch to help us with that. And AWS Batch is really just a tool to help us manage batch workloads on EC2 instances. And you can choose for Batch to either manage those compute instances dynamically by scaling out based on load, or you can control those yourself. And the steps are pretty easy. First, you have to define a compute environment, and you're given a choice. Either you can choose managed or unmanaged. And then you can also choose whether you want to use spot instances or on-demand instances. And then you can also specify how many virtual CPUs you need. And then once we've created a compute environment, we can create a job queue and we can assign a priority to that job queue and then also assign that job queue to our compute environment. Then finally, we create a job definition, and this can be a script or you can use JSON. It can include environment variables, mount points, container images, IAM roles, all those things that would need to be there for your batch job to run. And then really all that's left is just scheduling that job. And we go ahead and schedule it, and AWS Batch takes care of running that at the prescribed time. And if we choose managed compute environment, it's going to scale out the needed infrastructure and then scale it back once the job is done. Now let's look at some comparisons, because for the CSA Pro exam, just like with Lambda, you're not going to have to know how to specifically write step functions, but rather you should know when they should be used in relation to other services in certain use cases. So step functions should be used when we just need an out-of-the-box coordination of AWS components. And an example would be that order processing flow that I showed earlier. Now, you might also recall simple workflow service. Now, AWS is recommending that any net new applications take a look at step functions over simple workflow services, because simple workflow services is kind of an aging service. Step functions is the new service, so they're trying to steer people towards that. But they're very similar still, and they could probably be used to meet the same exact use cases and same needs. But in the context of the exam, typically you're going to see simple workflow service more aligned around manual steps or when there's manual intervention required. So when we would use it is if we need to support some sort of external processes or maybe some ultra specialized logic that's not neatly contained within the AWS landscape. An example of this may be a loan application process where we have certain manual review steps, and maybe those steps take maybe 2 weeks to accommodate. Not saying they can't be done with step functions, but just generally speaking, Amazon tries to steer people towards simple workflow service when there's manual intervention required or some sort of external processes that maybe are beyond the scope of AWS. Now you'll recall that simple queue service is a messaging queue, and it's best suited for store and forward patterns. We would use SQS if we had kind of an inbound workflow and we needed to dole that workflow out to worker processes, like maybe in an image resizing process. That's a good use of SQS, and we probably wouldn't use step functions for that. Now, AWS Batch comes into play if we need to have reoccurring tasks that really don't require heavy decision-making logic inside of them. So if it's something like, rotating logs daily on a firewall appliance, that's something that AWS Batch is well suited for, and we probably wouldn't use step functions or SQS or SWF. So again, on the exam, you're not going to have to know how to build each one of these things specifically, but you should know what use case they fulfill and when you would use one versus the other. Let's talk about Elastic MapReduce. Now, one thing to know is that Elastic MapReduce isn't a single product. It's a collection of products or a collection of open source projects wrapped together in a very manageable, easy to deploy manner. And one of the things that was very confusing to me when I first started learning about EMR was trying to understand all these crazy names and what the products did. And most of these are all open source and you could assemble them yourself. But that's the value add of Elastic MapReduce, is it tries to do all that stuff in an automated fashion, so it's more push button. So what I figure we would do is spend a little bit of time talking through some of the components of a Hadoop landscape so that if you hear these products, you know what they do and what function they serve. So starting in the center, kind of the core is Hadoop HDFS and Hadoop MapReduce. And that's where EMR gets its name. Hadoop HDFS is just the file system that the data gets stored in. It's a certain way of storing files that is conducive to data analytics and data manipulation. MapReduce is the actual framework used to do the processing of the data. Then we have Zookeeper, which is really just involved in resource coordination. It's trying to coordinate all these services to make sure they work together properly. We have Oozie, which is a workflow framework. We have Pig, which is a scripting framework. We have Hive, which is an SQL interface into our Hadoop landscape. We have Mahout, which is a machine learning component. Then we have HBase, which is a columnar database for storing Hadoop data. We have Flume, which is very useful for ingesting application and system logs. We also have Scoop, which can facilitate the import of data into Hadoop from other databases or other data sources. And laying all over the top of this, we have Mbare, which is a management and monitoring console. Just remember that there are two main pieces of Hadoop here, but all the rest of these things are more or less like add-ons. Then you also have companies that provide enterprise support and professional services, and they also contribute to these open source projects as well. Two of the most famous are Hortonworks and Cloudera. So I hope that clarifies a bit the parts and pieces of a Hadoop landscape. So as I said, Elastic MapReduce is really just a managed Hadoop framework for processing lots of data. Now it also supports Apache Spark, HBase, Presto, Flink. These are other open source projects that have various features and benefits. It's most commonly used for log analysis, financial analysis, or anywhere where you have a massive amount of data that you need to process. And especially in situations where you're extracting, translating, and loading the data into another platform. Now in EOR terms, a step is a programmatic task that gets performed on the data. For example, maybe we have a step to count words in a certain document that got sent into EMR. A cluster is a collection of EC2 instances that have been provisioned by EMR to run your steps. And here's what it looks like. We have a master node, and then we have some core nodes, and those core nodes have the HDFS storage, so they can persistently store your data. And then you also can have these task nodes. Think of these task nodes as just worker nodes. Their storage is ephemeral, so you can't store anything on them, but they're just there to work on the steps. And this is how you can scale out EMR to process many, many terabytes of data very fast. Here's the process in a little bit more detail. We have our steps. One could be a Hive script. If you remember, Hive is just an SQL interface into Hadoop. Step 2 may be a custom jar that we've created in Java. Step 3 may be a Pig script, and Pig is just a scripting language that we can use to do stuff in a Hadoop environment. And then at the end, we spit it out into an S3 bucket. So again, you're going to use this for just massive amounts of data. Let's say you need to collect all your logs and then scan through the logs to identify anomalies or problems that you want to flag. EMR is a pretty good way of doing that. For auto-scaling groups, you're going to have to know the different scaling options and policies and when those would be appropriate. You need to have a really good understanding of the limitations and differences between horizontal scaling and vertical scaling. Know what a cooldown period is and know that it's different than a health check grace period. And also know how cooldown might impact your responsiveness to demand. For Kinesis, the exam is likely to be restricted to just the data stream use cases for Kinesis, such as data streams and Firehose. And you should understand the shard concept and how partition keys and sequences enable shards to manage data flow. For DynamoDB autoscaling, you should know both the old and new terminology of a partition key, and a sort key. You should understand how DynamoDB calculates total partitions and allocates RCUs and WCUs across those available partitions. And conceptually, you should know how the data is stored across the partitions. For CloudFront Part 2, you should know that both static and dynamic content is supported, and understand all the possible origins and how you can set up multiple origins using behaviors. You should know some invalidation methods, that it supports zone apex, and the geo-restriction options. So for SNS, you should understand a loosely coupled architecture and the benefits that brings, and know the different types of subscription endpoints supported. For SQS, you should know the difference between a standard queue and a FIFO queue, and know the difference between a pub-sub architecture versus a message queuing architecture. For Lambda, you should know what serverless is in concept and how Lambda can facilitate that, and know the languages supported by Lambda. For simple workflow service, understand the difference and functions of a worker and a decider, and know that it's best suited for human-enabled workflow like order fulfillment or procedural requests. For Elastic MapReduce, you should know the parts of a Hadoop landscape at a high level, and know what a cluster is and what steps are, and understand the roles of a master node, core nodes, and task nodes.
When it comes to step functions, you need to know that they're just a way to manage workflow and kind of considered the successor of the AWS Simple Workflow Service. They also support some tasks, sequential and parallel steps, branching, timers, pretty flexible, very useful in serverless architectures. Now, AWS Batch comes to the rescue when you're in need of running batch processes on a periodic basis and you don't necessarily want to manage a server or a cron job or scheduler or something like that yourself. Because AWS Batch takes care of provisioning the EC2 instances and tearing them down when the batch processes are done. For the serverless application model, just know that it's sort of a front end, a nice front end for cloud formation, and it allows you to test serverless applications locally, which is hugely beneficial when you're trying to figure out what's wrong with your application. And do know that AWS SAM is different than serverless framework, but AWS SAM is a serverless framework. Now, for auto-scaling, it can be confusing because some of the terms are the same or very similar. But conceptually, just know what the difference is between EC2 auto-scaling versus application auto-scaling versus AWS auto-scaling. And we covered that in the lecture. You should know the difference about the options you have as far as scaling policies, and know the difference between horizontal scaling versus vertical scaling. And I can almost guarantee that there's going to be a question or maybe a couple questions on the exam about cooldown period. So know what that is conceptually and know how that might impact your ability to scale.
Remember to read through the white papers that I've linked in this lesson. If you're watching on a browser, they're going to be over here. And if you're watching on a mobile device, they're going to be down here when you put the device in portrait mode. Now, elasticity is going to drive a lot of other benefits from the cloud, such as cost and agility. So it's really a huge enabler for many other things. And you should also be thinking now about architectural designs in terms of cloud first. Even if you're never going to deploy to the cloud, in most modern data centers, we're moving towards modular workloads to support things like Docker or Cloud Foundry. And these things allow us to scale horizontally just like in the cloud. Now, if you're in a brownfield situation, think about items that will help you migrate closer to that cloud-friendly environment, like service-oriented architectures or messaging architectures and canonical data models. Those will all help you migrate when and if you get ready to make the move. Don't let the excess of resources permit sloppy design. Efficiency is still key as it translates directly into cost savings and customer satisfaction, whether it be on-premise or in the cloud. And by this time, you should be incorporating a microservice concept into your roadmap and leveraging business process API concepts as well, because that's going to drive a decoupling and also simplification and separation of concerns. All right, here's your challenge question number 1. Just like last time, when the question comes up, I want you to pause the video, give yourself 2 minutes, and try to come up with the best answer. And then after that, I'll come back and we'll talk through the answers. Here's the question. Okay, welcome back. Well, fans of the HBO show Silicon Valley might recall this seafood app where Jin Yang's app, originally created to share his grandmother's octopus recipes, was twisted into a Shazam for food during a pitch meeting. Well, that idea was actually rooted in a real application called MealSnap that was released by a company called Daily Burn back in 2011. And the app advertised that it would do much the same thing as this app. But like in this scenario, the artificial intelligence wasn't up to par. Rather, when the user snapped a photo, the app would route the image to Mechanical Turk, which is a microtasking market where companies can pay humans to do tasks. And in this case, MealSnap was relying on a human to decide what the food was. Then Daily Burn would use that classification to look up nutritional information. The problem is that Mechanical Turk workers could only identify food generally, like chicken or banana. So the nutritional lookup wasn't all that accurate at all. And before long, the app disappeared. So back to our challenge here. Really, the main thing that this question is asking is how are we going to best architect for this scenario? Again, one of the things I like to do is go through the answers and see if we can eliminate any of those. So if we go up to option A, we're going to create a PubSub architecture supplying the analysts with a custom program so that they can use to receive images pushed from SQS. If you recall, SQS is a messaging platform, and it's not really considered a PubSub architecture. That's more the realm of SNS. And additionally, messages don't get pushed from SQS. You have to pull the queues for those messages. So I think we can eliminate option A. Now again, scanning down through the options, option D looks a little bit strange to me. And the reason is because I know that Simple Workflow is much more of a statusing framework than a true workflow engine. And also, I don't really recall any feature called weighted routing. So I'm going to eliminate that one too. So right off the bat, we've eliminated two. And if we go back to the question, there's an important detail that we should pay attention to here. The pictures that people are going to take are high resolution, making them multi-megabyte pictures. So that should be an important clue here as to which direction we might want to be going towards. SNS has a certain size limitation on its message. In fact, SNS's limit is 256K. So we can't accept multi-megabyte files that way. For Kinesis, the maximum inbound message size is 1 megabyte, which is large, but it's not big enough to accommodate our multi-megabyte pictures. So the best option I think we have here is option E, where we would save that image out to S3, and then we would use SQS as a sort of worker queue for that image. Okay, welcome to challenge number 2. Same process. You'll have 2 minutes and then see after that. Okay, welcome back. Again, let's start going through the answers and see what we can maybe eliminate, what's reasonable and what's not reasonable. So starting with A, the default cooldown time for scaling might be too long. So we could create a scaling specific cooldown that overrides that default time. Well, that seems like a reasonable suggestion, as perhaps maybe we need to scale more aggressively to meet the need. So let's set that one to the side. Now option B is your internet gateway has become saturated. We should create a new VPC and an ELB with its own internet gateway and route the traffic equally to either EB. Well, internet gateways aren't susceptible to saturation. They really have no bandwidth limit. So I don't really think that's potentially a cause here. So I'm going to mentally set that aside. So option C says, in essence, we should implement scheduled scaling. The problem is that our demand is unpredictable. So scheduled instances won't really help us out. And it could probably lead to some excess sometimes. So I'm going to put that one to the side too. Now D says customer demand is not stable enough to properly trigger scaling thresholds of your existing scaling policies. We should implement a step scaling policy configured around CPU utilization. Well, that does seem like a reasonable suggestion. Let's keep going and see if we find anything better. Option E says our launch configuration is set up to launch undersized instances. We should edit our current launch configuration to launch larger instances. Well, the problem is that once you create a launch configuration, you can't edit it after it's been created. And I think AWS does this so it doesn't have to worry about validity dates of when certain launch configurations got changed or versioned. So right now they force you to create a new launch configuration and assign that new launch configuration to that ELB. Now, if we change this to say we would create a new launch configuration, this would be a good suggestion. Option F says we need more dynamic web capacity than our current configuration, so we can create a new launch configuration of smaller instances and implement a step scaling policy with a shorter cooldown period. The flaw with this is that step scaling policies don't have a cooldown period. Rather, they have a warm-up period where you can specify how long to allow your new instances to come up before another step scale can be triggered. So going back to the answers that I like A and I like D. So those are my final answers. How'd you do? Okay, hello Cloud Gurus. Welcome to the lab for architecting to scale, and we're going to do some auto scaling experiments. So you are consulting with a pharmaceutical company that's new to AWS, and every night they have these series of jobs and calculations that run against data that they uncovered in their day's research. Now, some days they have lots of data and some days they only have a little bit of data, so they need some sort of extensible scalability. They do have some knowledge about scalability on AWS, but they're kind of skeptical that it's going to work for them. And since they're scientists, they want objective proof that scaling works. So your task is to design and conduct an experiment to show how scaling works in the most cost-effective way. So let's break this down. First, we're going to have to design an experiment to demonstrate auto scaling to the scientists using cost-effective methods. Second, we're going to have to build the scenario that simulates heavy computational load so that we can trigger that scale out process. And then we also have to demonstrate scale in as that load diminishes. So if you're choosing the expert level path, this is where you pause the video, you go and just build this thing. Then come back, resume the video, and you'll see what I did in this case. Again, there's no right or wrong answers. There's many different ways to do this, but you'll just see one option. If you're intermediate level, the next slide is going to give you some hints that may help you get started. So regarding sequence number one, task number one, the hint here I'm going to give you is X marks the spot. For number two, sometimes stress is good. And for number three, there's a very interesting dynamic here. Those are all the hints I'm going to give you. You can pause the video and go build something. If you keep watching, I'm going to go into the walkthrough where you're going to see how I built this. So if you took the intermediate path, then you'll remember that I gave you a hint on how to build this environment. And I said that sometimes stress is good. Well, in this case, it's very good because it allows us to simulate, or it actually produces, high CPU load that we can use to trigger scaling events. I'll show you how it works with a little demonstration. On the left-hand side, I'm going to use top, which just monitors processes. And then I can issue the command stress, decide how many CPU processes I want, and what's the timeout. In this case, I'm telling it to run for 15 seconds. Now you can see on top, we've just consumed 100% of the CPU. So we can use this little utility to generate artificial load on instances and force them to scale. So we can get started on our experiment by going out to EC2 from the console. Then under launch configurations, we're going to create a launch configuration. I'm just going to pick a normal Amazon Linux AMI. And just for kicks, I'm going to use M5. M5 large. And because one of our objectives is to have the most cost effective, I'm going to use spot instances, and I'm going to put a number that's well in excess of the going rate. I also want to enable detailed monitoring, and I'll explain a little bit more about why I want this later. These instances don't need public IP addresses. And also I'm going to insert a startup script, and you do that in user data. It can just be a bash script in this case. What the script is doing is it's doing an update. We're installing the stress utility and then launching stress with a timeout of 10 minutes. So in essence, this is going to start up and then just burn for 10 minutes at 100% CPU. So now that we've created the launch configuration, we can go create the auto scaling group. And I can select this from the launch configuration I just created. I'm going to configure all subnets just to make sure that I have plenty of capacity for my spot instances. I'm going to change the health check grace period down to 60 seconds, and I'm also going to check the CloudWatch detailed monitoring. Now I want this to scale between 1 and 3 instances, and I'm going to use a dynamic scaling policy here. I want the target CPU rate to be 60%, and I'm going to say that the instances need 60 seconds to warm up. Now I'm finished, and as soon as I hit that create auto scaling group, AWS is going to go out and start provisioning my instances. Now, one thing to note here is the default cooldown period. I'm going to lower that to 60 seconds. But unfortunately, because it's already started trying to provision one of my instances, that instance is going to have a 300-second cooldown period associated with that. And we'll see what that looks like later in our video. If I go to my activity history, we've already initiated a spot request. And you can see I have an instance coming up. Now, just so we can tell our instances apart, I'm going to give this the name of scale 1, and we're just going to wait a bit. So now our desired number is at 2, and that's because we've been at a high enough CPU utilization that that's triggered the CloudWatch alarm to spin up another instance. And again, it's going to create a spot instance request. And you can see it's pending, coming up right now. And I'm going to give this the name of scale 2. And you can see our first instance, it is pegged out at 100% and it's still going. Now we've triggered the third instance and the CloudWatch alarm has gone off, and we're trying to provision another spot instance. If we go over to monitoring for our scale 2 instance, you can see the rapid climb up and it's at 100%. But our first one has finally reached that 10-minute timeout and it's dropped off. So we should expect the overall aggregate CPU utilization for the fleet to go down. And that's exactly what's happened here. Our desired instances are 1, and so it's terminated 2 of the other instances. And you can see our CPU utilization really dropped off. So we still have instance number 3 left. You'll notice that it terminated 1 and 2 before considering terminating 3. There's a way you can configure that in termination behaviors, but in general, it'll terminate the oldest first, but it also tries to balance the terminations across AZs. I can manually go in here and put a minimum of 0 and a desired capacity of 0. And as you might guess, that's going to completely shut down the last remaining instance. And so it's shutting down now. Now we can take a look at the profile. What actually happened during our scaling events? So when we first created our auto scaling group, it immediately launched one instance, but you can see there's about a 5 minute or so time period between when it originally launched instance 1 to when it launched instance 2, and subsequently it very quickly launched instance 3. And that's because what I told you about the cooldown time. So that first instance had a cooldown time of 300 seconds. And that just means that AWS is not going to do any other further scaling events until that cooldown time elapses. And the idea is that you want to stabilize the load. You get the new machine in the landscape, make sure it's settled, make sure it's absorbing traffic, and then reevaluate the need to scale. By reducing that down to 60 seconds, you can see the step from 2 to 3 happened more or less within about a minute. Something else to note here is you'll notice my granularity for measurement is at the minute period. And that's something you only get with detailed monitoring enabled with your EC2 instances and your auto scaling group. Now, if I had just basic monitoring, then the granularity would only be 5 minutes. And so we wouldn't be able to see this minute by minute profile. So that's something to remember if you have the need to scale on a minute by minute basis, then you're going to have to use detailed monitoring because it provides that tighter granularity of minute level measurements.